So, I guess I have only one more big concept to go over, and maybe a couple other small things. Just some organizational things to mention. I think it's possible we can do makeup labs. If we do, it'll be next Wednesday. So you'd have to be able to come on an off day for it. We can't do makeup labs as late as Thursday or Friday. So I probably should have done makeup labs this week, but I thought I would need all the lecture time for lab. If we have time, I'm hoping we have time for the lab time this afternoon to go over. Did you look at the thing for the final I put up, the ACS practice thing? I think we can go over some of that this afternoon. I think we'll have time. So we'll try to do that. So I'll go over this last concept and maybe a couple other odd little things. And then hopefully we'll be time to do a lot of that. Next week, that lab final, I'm going to grade it and treat it just like any other lab. I think that's the way they typically do it anyway. But since I still have so many labs to give back to you, graded labs, it really is particularly unfair for you to be, for that to be a final, you know, and you'd have to do it all yourself. So I'll break protocol that much just to say treat next Tuesday's lab just like any other lab. You'll come in, I'll help you, you can ask questions, I'll explain things as you need. So there's that. Okay, test 4 next Tuesday. I'm going to come in tomorrow and do a bunch of grading, including your last test, and start getting test 4 together. So I'll get something of a practice test for you before Monday evening, like I did test 3. So I guess by Sunday night, I'll have a practice test for test 4. And then we'll come in next Thursday. We'll take the final in the morning. And yeah, I checked, we can't do labs that afternoon. So I expect to have your test 3 and most of your graded lab grades into D2L by the time we're here Tuesday. So you have a better idea where you stand. We still have test 4 and the final as far as big grades go. One more thing in case I forget. So I'll go over stuff, we'll take a break, then we'll come back in here during lab time. If I forget to say this before the break, if you need to make up labs, I've got a copy of the lab schedule here and another sheet here, a bunch of writing on it. When you get back from our break today, find your name and write down which labs you have to make up. Use this and tell me which lab it is, not just what day it was or whatever. So if we can organize makeup labs for next Wednesday, I know what we're going to need to do. But do that when we get back from break today. All right. So it is, let me write these down just so you know what we're doing. That extra sheet I just gave you, there is a section in our book that covers those two things. There's the front of the page and the back of the page. I thought those diagrams were better. That's from OpenStax. But I'll get to that in a minute. But let me give you, make sure this is on video. So I go to the edge. Figure 6.20, 6.21. Start with those and then section 9.5, section 9.6. There's a couple other things. We'll see if I get to them. So this is 6.0. You can ignore this. One of the things I've not gotten to that might be on the ACS test is this idea of a probability map. What I really want to show here, though, is I'm just bringing this up to say this is what the shape of s orbitals. So you've got you've got the nucleus, and then for the 1s, it's a spherical shape around the nucleus. And you can just picture, this isn't strictly true, but you can picture this sort of classical picture of the electron just zooming around in that orbital. And ultimately, if you just stared at it a while and traced it as it zipped around, you would get this image of a sphere. It's sort of like saying the electron is localized mostly in a sphere a certain distance away from the nucleus. And of course, you go to the next level up, the 2s, it's way bigger, and the 1s is on the inside. 3s, the same way, it's just bigger, so the electron's zooming around in there. S orbitals, I'll draw my diagram. If you look at the book a lot, you know the book doesn't use this type of diagram. I've said before, I wish textbooks still did it this way. So 1s, 2p, 2s, 2p. I always do it like this. Make these a little smaller. 2p, and then 1. This is 3D, 3P, 3S. So 1S, 2S, 2P, 3S, 3P, 3D. And the 4S actually starts here. And if you can memorize that much, that gets you started on pretty much anything. So these S orbitals are what's being pictured here, 1S, 2S, 3S. And then just outside the 2S, 2P, the p orbitals, if you want to picture how the electron zooms around, you can ignore this density map. One key thing here is p orbitals have these two lobes, so you can picture an electron zooming back and forth. It kind of stays in here and in here, so it's going kind of longitudinally, it's going around in there, just buzzing around. And it's one electron, or it might be two electrons paired. But that's the shape of the orbital. A lot of textbooks make the analogy to orbitals of planets going around the sun, or maybe the moon going around the Earth. Those are necessarily spherical. But these p orbitals just kind of have this longitudinal nature to it. And you can see here the way they've done it. If you think of a three-dimensional coordinate system, you've got your x, your y, and your z. Each one of these travel along one of those axes, so they're all perpendicular to each other. So that's worth seeing. It's 6.22. Oh yeah, okay, p orbitals. P orbitals are strange, and since I don't go into too much of the quantum mechanics, thinking of it this way isn't the best way to think of it. This is that density map I told you to kind of ignore. So this is saying that in these names, dxy, that's just in the xy plane, dyz, that's in the yz plane. So this is true. This one's kind of odd, and this one's kind of odd. But instead of doing that, just to save your thinking a little bit, notice that the p orbitals are symmetrical, where you've got along one axis, then you've got it along another axis, then you've got it along another axis. 6 lobes altogether. Think of d orbitals as 10 lobes altogether, and they're all symmetrically distributed instead of that weird way I showed you. That just helps your thinking a little bit. It's not going to hurt anything I have to explain to you, but chemistry's like this. There's, it starts out as a nice, neat pattern, and then there's the weird stuff, and then there's the exceptions. Every rule in chemistry is like that. In case you feel like I hedge every time I try to give you a definition, that's why. So I just kind of want to elide the weirdness with d orbitals. Just think of them as doing something similar to p orbitals, but instead of 6 lobes, 3 orbitals. There's, let's say there are 10. Yeah, 5. So 5 orbitals distributed in 10 lobes somehow. But that's me just trying to simplify things because it really isn't going to be that important for what I have to explain. And then now we'll skip to 9.5. We'll start doing what is really the last concept here. This is where I started last time and I started getting messed up. Get to this diagram. Hybrid orbitals are hybridized orbitals. But I'll start here. This is the way you would start learning, being able to do something with this concept. BEF2, if you had that in front of you, that Lewis structure, and you combine what we're doing today, again, you'll start seeing these molecules with the bonds here, and I told you before, we don't do ionic compounds that way. This is one of those situations where chemistry, you can organize things with the nice sets of rules, and then once you learn those rules, there's always the weird exceptions to the rules and the reasoning why. A lot of 1211, we give you these rules and act like they work 100% in any situation, and almost none of them really do. I told you before that if you have a metal and a metal, you have a metallic compound, which we don't even really draw structures for. If you have a metal and a non-metal, you have an ionic compound that we don't do this way with lines and connected things, because those are lattices of negative, positive, negative, positive. And then you have your non-metal to non-metal, which are molecules, which are covalent compounds, and those are the ones we draw this way. And I told you the quick way to decide whether you're looking at an ionic compound or a molecular compound is if it's a non-metal and a non-metal, you have a covalent compound, and if it's a metal and a non-metal, it's ionic. But that's not strictly true. The best thing to go by really, later in this semester we got to electronegativities and electronegativity difference, and the way you look at the difference and decide if it's 0 to 0.5, it's nonpolar. If it's 0.5 to 1.9 or 2, it's polar. And above that, it's ionic. If you took the electronegativity of beryllium, a nonmetal, and fluorine, beryllium a metal and fluorine a nonmetal, you would see that it's between 0.5 and 1.9. So there are exceptions. I guess really the better way, now that we've gone over electronegativities, to decide whether something's ionic or covalent is to use the electronegativity difference. But in general, I think even on the ACS test, it might just flat out ask you, here's a compound, it'll give you the formula and say, is it ionic or covalent? The first thing you want to think is you're looking for metal to non-metal for ionic, and non-metal and non-metal is covalent, and metal is metallic. But so I'm just saying that because you'll see some of these molecules I draw and you go, wait a minute, you said that would be ionic at the beginning of the semester, and then later in the semester we had electronegativities, and that's how I decided what was ionic and covalent. So this is just one of those exceptions that actually makes a molecule, and it's not an ionic compound. So anyway, so if you start here, and I said, what is the molecular shape for fluorine? Do you remember how to do this from last time? Or let's walk into it. How many electron domains are around the fluorine?
Fluorine?
4. You see it? Each one of the pairs counts, and then the bond with electrons in it counts. So that's 4. Beryllium only has 2. If I said, what's the molecular shape for beryllium, you would say linear. When it's 4, what do you call it? Tetrahedral. Okay, so if you can get that far, I'll say linear, tetrahedral. And this is the electron geometry, as I called it last time. There was that next step where you ignore pairs of electrons, and that's the molecular shape. But if I said ignore pairs of electrons here, and then what shape do you get? in some sense, I didn't cover this example last time, but really, this is really like a null case because it's only connected to one thing, and there's, if you ignore these pairs of electrons, there's kind of nothing there. Some books will call that linear, but we didn't talk about being connected to one atom. We started it being connected to two atoms, like this one, and called that linear, and then we went more and more from there. So, but by electron geometry, you would say this is tetrahedral, and this one's tetrahedral. If you can get that far, then there's this. If it's four things, you remember me saying this, if it's two things, it's sp hybridized. If it's three things, it's spp, but actually we say sp2. If there's four things around it, and this is, by electron, how many things around it? 4 would be spp, but we say sp3. 5 things around it, we'd say sppd, but really we write sp3d. And 6 would be spp, and then 2 d's, sp3d2. So really this is what we report. I just do this so you can easily see 1, 2, 3, 3. 1, 2, 3, 4, 4. 1, 2, 3, 4, 5, 5. 1, 2, 3, 4, 5, 6, 6. And of course 2 there. So what I want to do here is for tetrahedral, I'm going to say sp3. For linear, I'm going to say sp because there's 2. All right. Get this out of the way. All right, so if that's true, I'm just going to do, say, for fluorine, that's in 2, and beryllium is in 2. Okay. So beryllium's valence is here, and so is fluorine, so I'm just going to draw this part. So for fluorine, and I'll say the fluorine on the right, it's sp3, so there's your 3 p's and your s. Those hybridize and you end up with 4 equal orbitals. And now your 7 valence electrons so in a molecule, this is what fluorine is doing. It's sp3 hybridized orbitals. And this one's exactly the same as that, so this really covers both fluorines. So that's fluorine. Beryllium, sp2, so I'm going to take the s and one of the p's and hybridize those. And then I'm going to leave these 2 p orbitals here. So those are p orbitals, and these are sp orbitals. And these are all sp3 orbitals, aka sp3 hybridized orbitals. That's fluorine, and this is beryllium. So in this molecule, they're really like that. Beryllium has 2 electrons. I'll put them both there. I didn't put any up here. I'll explain what these do in terms of bonding and lone pairs. But I left these not paired because these need to pair with this electron in fluorine. I'll draw the other fluorine over here just so I have room to make some arrows. One of these and this bond, and they that's what this is. And then another one of these bond, and that's what the other one is. And in case you're wondering where these are, there's your 3 pairs. See what I'm saying? These equally distributed in space to make the tetrahedral shape. 3 of them have electron pairs, and one of them has that one electron that's being paired with the one from beryllium. So now you see where all the electrons are and what types of orbitals they're in. Another thing to mention here is think I have to draw this. If I were to sketch these, let me do like this. For beryllium, can I erase this? Let me erase that. So beryllium like that, you have, so this is the atomic orbital for beryllium, not in a compound. There's the s orbital, and you've got one p orbital like this, another p orbital like this, and then there's one more going straight out at your face, going straight out this way. I'm not great drawing three-dimensional things, so this slanted one is the one that's coming straight out the board. You with me? When they hybridize, one of those p orbitals, and I'm going to use the weird one so I don't have to draw it like that again. No, I better not. I'll use this one. So this S and this elongated P hybridize. Two orbitals go in, two orbitals come out, the two SP orbitals. So if I did the hybridization of, let me use colors here. It's this P and the S. Do a little artwork here. It's the S and this P come together and make two new orbitals that are 180 degrees away from each other. So this is an SP, this is an SP. And then this p orbital is still there, and the one going straight out at you is still there. So there's a pair of electrons here. Use one more color, so I'll do something. I've got colors. There's the pair of electrons in that bond. The blue one I'm indicating is coming from fluorine. Oh, I used yellow. I gotta make these yellow. So one from beryllium and one from fluorine. One from beryllium, one from fluorine. Same going to the other fluorine over here. So if I wanted to sort of sketch the orbitals, I can indicate it this way, and I can indicate it as a three-dimensional structure this way. This is just kind of a diagram. This is also kind of a diagram structure. This is the diagram of the actual orbitals. And now let me do fluorine, and I'll add it to this picture. If I did fluorine, just redraw it. Fluorine is like this. And if I drew fluorine, it's the same thing. 2s, one of the 2p, another one of the 2p, and then one going straight out toward your face. And you've got this going on when you hybridize it. You take this P, and this P, and that S, and you make, I'll do, so tetrahedral shape. Do it like this. Those two are in the plane of the board, and there's one going behind the plane of the board, and one going in front of the plane of the board. This isn't a very good diagram because we would usually do a wedge, but it's a terrible diagram because it's three-dimensional and it's hard to do that. I'm not a graphic artist, but this is SP3, SP3. So 4 orbitals go in, they hybridize, 4 orbitals come out, 4 equal orbitals, equivalent orbitals. All right. And if I want to put the electrons in, let's do, those are sp3. This has 1 electron, and these others have 2. So if I added it to this picture, I'll drag that down here, and I've got I'm just not going to try to do this 3-dimensionally, but that's the tetrahedral shape. If you wanted to sketch it, this is where the pairs are. And then there's another one just like that over here. But this is really tetrahedral, not flat like this. Oh, I should have made these blue. Whatever. Anyway, this is called our book doesn't do this, and I won't have you sketch these on test 4, and the final won't have you sketch these. It might sketch them and ask you about it. This is called a valence bond sketch. So just to give you an idea, these orbitals are actually empty. These are empty. But kind of what I want you to see here, because it'll be important for the next section, is this going straight up and down and this one going out towards you, they form a plane that just sort of bisects here between the 2 fluorines. So if you can kind of picture that, that'll help when I get to the next section. But there's a description of beryllium difluoride. Okay. So specifically beryllium here, they've used beryllium difluoride as an example of sp hybridization. I went ahead and showed you the sp3 because the fluorine is doing something too. So the next point here, they go to sp2 and sp3, and they start with there's a good CL5. It's hypervalent. I guess H2O. sp3. We'll use the example in the book BF3. sp2, okay, we'll do BF3 next. If you drew the structure of BF3, what's sort of the Lewis structure. This is boron now, not beryllium. And I'll go ahead and give it its... so these fluorines are just like the one I did before. If I said how many electron domains around the fluorine, you would say 4, and that would necessarily mean tetrahedral for the electron geometry. If I said how many around boron, you would say 3. So boron is, so that means 3 things around it. These are sp2 hybridized. 4 things around it. These are sp3 hybridized. We're still in the second shell for both of these. I showed you fluorine before. I'll do beryllium. Beryllium would be, boron. So atomic configuration of boron would look like this. And if you do sp2 hybridization, that's these hybridizing, and you leave the p there. So I'm going to bring those 3 down here, and we're going to leave that 1 p there. sp2, sp2, sp2. So to visualize this, you just look here and you use your knowledge of molecular shape or really electron geometry, not not molecular shape, to construct this. And then the three, you've got three of these bonds. All three of these go here, and the p orbital is empty. And you've got three fluorines. And I drew the fluorines before with that one extra. Each fluorine looks like this. So each one of these is what these are. So each fluorine is connecting to one of these. And you know this is trigonal planar. If I wanted to draw it, well, let me do this. Boron, the valence bond sketch, p orbitals, and then the one going straight out at your face. Okay, so that's the atomic. And then if you hybridize, should I hybridize? I'll take this one, I'll do what I did before, I'll make them a color. The ones I'm going to use to hybridize, they're all equivalent. I could use any, because I could take this thing and turn it in three-dimensional space. But it's, these I'll do. There's that p orbital, there's that p orbital, there's that p orbital, and then there's the s orbital. And it does not look like a sphere. Anyway, so it's only this white one that I'm leaving out of the hybridization. When it hybridizes, you get three orbitals go in, three orbitals come out, and you still have that. I've left the one that's up and down, so this p orbital is still there. Maybe I can kink this a little bit to look better. So here's our whatever. But this one's going straight up and down, and no, that's not the way I want to do it. I need to use, all right, I do those three. Yeah, let me start over. I want to use the two in the plane of the board so I can draw it right, for the things to be in the right plane. Hybridize the S, and that P and that P. This is just so I can draw it on the board well. And then this is the one going straight out at your eyes. And then I hybridize them, I get sp2, sp2. And this is for the boron. And then the one going straight out at your face, it's still there, but it's going this way perpendicular to those three. I guess I'll still kind of indicate it. That's the one going straight out the board. And then the fluorines are here. It's got the four tetrahedral lobes that I really can't fit into the plane. And then it's got what we call orbital overlap, where those two electrons are that are paired. One electron coming from beryllium, one coming from fluorine. This one from fluorine and this one from beryllium. And then you have that same thing going on with these, going to fluorine. Same as this. This out of the way. So what to grasp here is that last p orbital, and it is empty. When I start having something left over in here is when drawing all this is worth seeing. But these are on the plane of the board, and then perpendicular to that is that empty p orbital. So that would be the valence bond sketch. So far, really, sketching like this is just another way of representing these. Okay, that's sp2. Let me focus on a central sp3. Yeah, carbon is good here to do. So CH4, CH4. If I drew the Lewis structure of CH4, we draw it like this. And if I said how many domains around carbon, you would say 4. So you would think sp3. So for carbon, here's your 4 valence electrons. When it hybridizes, all of them hybridize, sp3, and you put your electrons back in. And now you can see that all of these are available for pairing. And you know that from looking here. It's got 4 covalent bonds. 1, 2, 3, 4. So each of these need to have 1 electron in them. Hydrogen is just 1s, like that. So if I drew this, and there's no hybridizing here, because it's just in the S. All right, and if I drew this part, and again, this should be tetrahedral, but I'm not going to try to draw it 3-dimensionally. And you have hydrogens out here, and really what's going on is the hydrogens aren't hybridizing. They're just that spherical s orbital or overlapping an sp3 orbital. So you use your logic thinking this way and then thinking this way, and then you fill in your electrons based on what you see here. And then you're able to sketch it. This should be tetrahedral, overlapping sp3 and s. And of course it's tetrahedral, so those hydrogens are also tetrahedral. But you see the overlap. This would be the valence bond sketch. All right, I'm going to stick with carbon compounds. So far, you haven't seen any double bonds or triple bonds. Everything we've done were just single bonds. So this next section, they go to hypervalent here. Is that when you involve the d orbitals? Hypervalent. Oh no, they just go on to well, I'll do these. Hypervalent seems the wrong way to name this section to me. But PCl5, let's do that. So start by looking at the Lewis structure. For these, I will give you a Lewis structure if I'm going to ask you all this. If I want you to draw a Lewis structure, I'll give you the backbone and you can go from there. 1, 2, 3, 4, 5, 35, plus 1, 2, 3, 4, 5. So 40 total electrons. 2, 4, 6. 22, 24, 8, 30, 40, okay. So that would be the valence. So when it's 5, it's going to be sp3 1d. Phosphorus is 3. So it's these. This is just always going to seem weird that there's a 4 starting there. But it's those that hybridize. I'm going to leave the 4s out of my diagram here. All right, those will hybridize. This, all of these, and one of the Ds. We got 5 lines, and we still have 4 of these left. So 3D, and this is SP3D, SP3D. So 5 orbitals go in, they hybridize, they become this, and these are left over. And phosphorus has 5 valence electrons, and you see 5 of these single bonds. So they're all going to be in here. And again, the p orbitals are empty. If I sketched it, I would have do you remember what you would call this molecular shape? There's 5 things.
Trigonal bipyramid.
Trigonal bipyramidal. And these are tetrahedral, like that. I showed you the chlorine before that looks like this. Each one of those chlorines, that's one of the electrons in the bond, and then it's grabbing one of these. So I'm not going to finish it, but that would be the SP sketch, I mean the valence bond sketch. So PCl3. And I would say just ignore those other d orbitals. I'll draw them. SF6. BRF5. I'll do BRF5. SF6 is just going to have, if I did SF6, then I would just have another one of these, another F. I would hybridize that, which would leave me S, 6. 1, 2, 3, 4, 5, 6 valence electrons for S. You have those left. And each one of these would be going to one of the Fs. F would just look just like this, except for it would be in the second level instead of the third. But this one, what did I say? BR5, BRF5. Um, 35 plus 7 more is 42. So now we end up with, we're going to end up with a pair here. That's why I wanted to do that one. So F I showed you earlier. All right, let's double check. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42. That would be the Lewis structure. And BR is 4th level, but instead of drawing all this, I'm just going to go P 4P and all right, how many electron domains around bromine?
5.
6. There's 6. Do you see it? Each one of the lines plus this makes 6. So if it's 6, it's going to be P3D2. 1, 2, 3, 4, 5, 6. It's those that hybridize. 1, 2, 3, 4, 5, 6. And that leaves us 3 d orbitals. I'm going to leave the 4 off. D, 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 SP, 3, D2, all the way across. And then bromine 2, 4, 6, 8. So there's 10 electrons around this bromine. One, 2, 3, 4, 5, 6. So there's 12 around it. And only one of these 2 electrons are on bromine. Only one of these 2 electrons are on bromine. And there's 2 here as a pair. So one of these has to have a pair, and the rest all need to have one. These are the 5 electrons bonding with the unpaired electron for fluorine. So I could draw the valence bond sketch, and it would just be, these would all be tetrahedral, and then this would have 5 lobes coming out from it. But like I said, don't think about the geometry once the d orbitals come in. It is trigonal bipyramidal, so maybe you can see it in your mind. But you won't have to draw these. Anyway, hybridized orbitals are what happen for bonding in many cases, not in every case. Okay, hypervalent. Hypervalent, they're saying, is those that have the expanded octet starting at phosphorus. Okay, I want to get to, I said 9.5 and 9.6. Yeah. Did I say 9.4 or 9.5? Let me be sure. Whatever I wrote on the board up here to begin with, it's 9.4. 9.6. This was atomic orbitals, just the S and the 3 P's. Hybrid orbitals, and this is related to multiple bonds. That's double bonds and triple bonds. This was all single bonds. And covalent bonds overlap. Oh, I guess I didn't cover 9.4. I said 9.5 and 9.6, is that right? Okay, not really 9.4. This was chapter 6, whatever that was. Wherever those figures were. All right. 9.4 just mentions that idea of overlap. Okay, so multiple bonds now. And now that page that I gave you, I'm going to do, for the double bond, I'm going to use this molecule. That's the one I had on that page. Let me get me a copy. So this is what I'm going to do next. And then I'm going to do the triple bond here. So I guess you can use this page really for this. C2H4. The Lewis structure look like this. Oh, let me take a quick aside here and okay, ignore that for a second. Let me just draw a big molecule. a little crazier here. Oxygen, nitrogen, what do I not have? I guess I could stick boron on there. No, this is good. I'll keep this orthogonal. 1H, 1H, nothing. Just H's here. I'll put the pairs in, but they're not really necessary for what I'm going to describe. Okay. Anywhere you see a single bond, sigma, we call it a sigma bond, and that's the Greek letter sigma. These are kind of synonyms. Sometimes we use the symbol, sometimes we say it out loud. And then one sigma and one pi bond. And of course the symbol for that is what you know is pi. Triple bonds are one sigma and two pi bonds. So I took an aside to do this because this is such an easy thing to see. If you're given the whole structure, you can see it right in front of you. I'm going to color the pi bonds with this color. So this is correct the way it is, but let me show you where the pi bonds are. So that's one sigma and one pi. That's one sigma and one pi. This is one sigma and two pi bonds. Do them like that. And the rest of those are sigma bonds. So you can look at something and count the sigma bonds and count the pi bonds just by that. All the singles contribute to the number of sigma bonds. And then any of the multiple bonds, these are the multiple bonds. It's either going to be 2 or 3 for multiple. There's no such thing as quadruple bonds. And if it's 2 lines, one of them is sigma and one of them is pi. Sigma pi. If there's 3 bonds, still one of them is sigma and 2 of them are pi bonds. And that's what this section is on. What is the hybridization scheme and where are all the electrons and what does the sort of sketched out valence bond sketch look like? But that's a very easy thing to grasp just looking at a molecule. So grasp that before I go into this because that's very obvious. If you're asked a question like that, it's just easy to count them up. I could add to here how many lone pairs are there. Lone pair there and 2 there, so there's 3 lone pairs. Okay. So having explained that, sigma starts with an S, and that symbol is the Greek letter for S. Those are pretty much associated with S. But I'll tell you what the twist is in that. Pi bonds always come from p orbitals, so it's not a mistake that pi is the Greek letter for p, and the word pi starts with p. Same with sigma, but I'll show you where the twist is. Okay. Double bond. One of these is a sigma, one of them is a pi. So that's where we're going. If I said how many electron domains are around this carbon, what would you tell me? Around this carbon. 3. There's 3. This counts as 1, 2, 3. So for electron geometry, this carbon, square planar. For hybridization, because there's 3 of them, it's sp2. So, and this is true of both carbons. These carbons are in the same bonding situation. one double bond and two single bonds. So both carbons are doing this. 4 valence electrons in carbon. Okay, that's the atomic picture. If I drew the atomic picture, it's this. And then the one coming out at your face. There's 2 electrons here in the, almost said sigma, in the s orbitals, and then 2 of these have 1 electron. So this one has 1 electron, and this one has 1 electron, and one of the pi bonds is empty. But the hybridization, if you're going to do sp2, I'm going to take those and go 1, 2, 3. 3 go in, 3 come out. These are sp2 and 1p. There are 3 sigma bonds up here. So you know you can only have 1 electron in each of these. And now here's where the pi bonds show up. Everything I've showed you so far, the p orbitals were empty. So there's your 3 sigma bonds. And then your 4th electron goes there in one of the pi orbitals. So you got 3 sp2s and 1 pi. And now if I drew, I need enough space over here. So I'm drawing the carbon on the left, but these are equivalent really. Carbon, and so here's my 3 lobes. And I'm doing them in the plane of the board because it's square planar, so that's in the plane. And that last pi is coming straight out at you. I'll do it weird, elongated like that, but that's the one coming out straight out of the board. All right, and the carbon over here, I'll say these are sp2 orbitals. And then the carbon over here is the same way. I'm going to do one of the sp2s like this. And then and it has a leftover pi bond going straight out at your face. Let me do this a little bit skewed. So these are the sp2 orbitals. Double those up. Okay, sp2 orbitals. And you actually do have 2 carbons. So those are sp2. So 1 electron from here, 1 electron from here are bonding to make this bond. The hydrogens are out here, and they're still just that 1s, not even hybridized. Hydrogen. You're getting 1 electron from hydrogen, and these 4 hydrogens, those 4 hydrogens, they bring 1 electron along, and each of those hydrogens are bringing their electron along to make these bonds. Hydrogen. I should have 1 S here for the hydrogens, but I'm just saying H. So those are the ones bonding. So there's all these bonding things. Here's the thing. Here's where the pi bond comes in. Pi bonds have those 2 lobes going on either side of the atom. These are coming out straight out of the board. And these are making a bond too. But here's the thing, and here's the key about what a sigma bond really is. The sigma bond has them going straight towards each other, and they're overlapping right in the middle of the 2 atoms. Pi bonds, you got 2 lobes to this pi bond, pi orbital, and 2 lobes to this pi orbital. Each of them have an electron in them. Those electrons pair. So this electron's going back and forth through here. And it's really lobe-shaped like that. And this one the same thing, but they can pair with each other. And what they do is make a bonding orbital like this. And just to specially note, this bonding orbital, well, I've made this a little ugly. Those two lobes are one pi bond. I would just say this is p orbital and a p orbital. But those two lobes make up that pi bond that's in there. And that's what this page is trying to show you. This side with the double bond. They drew theirs, instead of in the plane of the board, they've got them like this, but they didn't depict it too well. And these two SPs are like this, and the pi bond. So they're drawing the pi bond in the plane. Okay, so that's how double bonds work. Flip the page over, and now we'll do the MacDaddy, where you've got two pi bonds. So we're going to start. Again, you start with the Lewis structure. On the test, I'll give you this. This is C2H2. If we drew the Lewis structure, we would just draw it like that. How many electron domains are around this carbon? Two. So this is sp2 hybridized. No, sp hybridized. Carbon 1, 2, 3, 4. There's the atomic situation. And if I drew it like this, I did this before, I guess, but there's two electrons in the S. There's one electron in one of these. And there's one electron in this. And of course, there's an empty P like that. There's the empty P. Okay. And then SP, with two leftover P's. All right. So I'll have to erase that. And then the four electrons. You look up here and you go, you got to have three electrons. Two of them are pi bonds, so two of them go up here. And then you've got one bonding to this carbon for the sigma bond, and another going to this carbon, so there's those two. But there's where your four electrons go in the hybridized scheme. One each. And if I drew the carbon, now I'm going to draw linear 180 degrees. Those are the SPs. And I'll draw the electrons like this. One electron in each of those. Now you have one of the leftover pi bonds there, and then there's another leftover pi bond here. And these are the P's. It's pi, that's pi. And each of these have an electron in them. So there's an electron, well, that one's really going out and behind the board, and then this one going up and down, and then you have these two bonding orbitals. So these two things together make one orbital. These two things together make one orbital, and then these are two separate orbitals. So there's your four orbitals. And the other carbon, I'm going to draw just like this one. Getting fancy with my electrons here, but SP, it's exactly the same. So this brings another electron together. So now you've got your pair there. In the same situation, leftover P, leftover P. All right, and then over here where you have an electron, you have a hydrogen with the s orbital, a hydrogen with the s orbital, with those two electrons. And now one electron here, one electron going in and out, one electron here, one electron going in and out. So now what you get is these that are coplanar like this, going straight up and down, they form that sort of banana-shaped bond, and this is what's being depicted in that last. Kind of shaped like that. I'm going to completely erase these. These that are going out in your face. So I'm not doing a great job of this, but all of this is that banana shape. And then, so that makes one of the pi bonds. And the other pi bond is this same lobe thing, but there's a lobe out in front here and a lobe in back. That's what that is depicting. Okay. And I think good, the video's still going. It is. In the next hour, let's just go through as many examples as I can stand. 9.5 and 9.6. That's 9.3. 6. 9.4 and 9.5. I did BF3, didn't I? You have that in your notes? Let's not do that. Okay, let's do SCL2. SCL2. All of these, they're not giving you the Lewis structure. For any questions like this, I'll give you the Lewis structure. I'll have you build a Lewis structure separate, and then separate questions when I get into this. I'll just give you the Lewis structure. Say SCL2. All right. 20 electrons, 4, 6, 12, 14, 16, 18, 20. There's your Lewis structure. Let's focus on the sulfur. How many electron domains? So what's the hybridization? SP, SP2, SP3. 4 things. SP3. SP3. So sulfur. 6. 1, 2, 3, 4, 5, 6. Yeah. Okay. That's the atomic configuration. SP3. We're going to look up here, and we see that sulfur is making 2 sigma bonds. 2, 3. And it's got 2 pairs. So it should just add up like this. The valence electrons, the 6 valence electrons go 1, 2, 3, 4, and now you go back and start pairing them 5, 6. And then you can see 1 electron here, 1 electron here, and there's your pairs. So your pairs, and you got 2 of those. Chlorine, what's the hybridization there? How many electron domains? 4. 4, so it's also, this is the sulfur. If I did chlorine, it's got 3 pairs and then 1 electron by itself. 7 valence electrons, 1, 2, 3, 4, 5, 7. So there's where your bonding is coming in for each one. Hybridized orbitals, what do you next? So the sketch will be